Hello, everyone, and welcome to today's graph reading group.
Where Yilun Chu, also here from MIT, introduces this PFGM++ and discusses diffusion models, flow matching, and all the advantages that come with PFGM++.
Okay, thank you, Hannes, for the introduction. Hi, everyone. I'm a fourth-year PhD student at MIT, advised by Tommy Yakula. And today I'm going to present our two recent works based on physics-inspired generative models. They are called Poisson Flow Generative Models. And the other one its extension is called Poisson Flow++. And these two works are joint works with Ziming, Yonglong, Shangyuan, Max, and Tommy. So recently we have witnessed the significant improvement in image generation. Here is the FID score, the progress in FID score in recent years. The lower FID score is, the better image qualities is. So we can see that the FID score consistently decreased from around 30 to close to 0.
What happened in the middle of 2020?
2020.
Yeah, that's a jump.
I guess, I see. There's a new architectural design. It's called Big Gang. So they redesigned some critical component in the architecture of image generation.
Okay.
Yeah.
And
so,
if we were to zoom into this
Yeah.
a little bit, like everything since 2021 maybe, would we see diffusion models improving this FID?
yeah, I guess improving from 5 to 3. So it's
Okay.
it's a bit I would say improving from 5 to 3 is still a quite nice improvement.
Yeah, of course.
Yeah. So, but so the best performing models today is called PFGM++, and we will cover it in this talk. And yeah, and another paper used human error rate to assess different generative models. And human error rate means how often does a human being classify the generated images into real images. And we can see that PFGM++ achieve the highest human error rate, which means that it generates most realistic images.
Yeah, let me note here, right? This is like the gold standard evaluation, so to say, right now, or maybe possibly the best evaluation that one can do in terms of image quality, right? FID is, I mean, we look at how well do some embeddings, or like what's the Wasserstein distance between some embeddings, or the a Gaussian giving by some embeddings of our images and the Gaussian of some embeddings given by the dataset. What's the Wasserstein distance between those? And that's maybe not exactly what we care about, especially if we use the training data and calculate our FID score to the training data. And now we have this human error rate evaluation of image quality, and this I find is maybe the best metric that we have right now. And of course we can't really compute it, but these people, like those were NVIDIA people that did this experiment.
Startup called Layer 6. Layer 6.
Yeah, layer 6. Some company did this experiment where they paid many humans to get this, or to label images, generated images, as generated or not, and to see how often the humans were what do you call it? The humans were confused.
Classify generated images into real ones.
Are deceived. How often humans were deceived. Yeah. All right. Yeah, sorry for the interruption.
No. Thanks for the background information, Hannes. Yeah, and before going into the Poisson Flow++, I will first briefly cover its predecessor, Poisson Flow Generative Models, to give you more backgrounds about this work. And yeah, in Poisson Flow Generative Models, we interpret the n-dimensional data as electric charge. as we can see in the leftmost figure, when we have an arbitrary charge distribution, its electric field could be quite complicated and have high curvature. But as we zoom out, the charge distribution looks more and more like a point charge, and the electric field emitted by a point charge is very simple. It's just radial in every direction. And this radial electric field could naturally form a uniform flux density on a large sphere, because each radial electric field is perpendicular to this sphere. So it seems that we can design a valid generative models by first uniformly sample from this large sphere, and then we evolve the sample back to the data by following the electric field lines. But is this a valid generative models? The answer is no. Here is a counterexample. Let's say we evolve the samples along the electric field, and all the samples will eventually end up at the origin if our data distribution is a 2D uniform sphere.
Okay, so
uniform disk.
What we would want is like a few samples. Why does this not work? Yeah, a few samples here,
Yeah.
a few samples
Yes,
here,
yes.
and some here.
Mm.
But if we train our model, what we want end up with is just putting everything to
Yeah.
the mean of
Yeah.
this
Yeah.
of our actual distribution.
Ideally, we want the samples spread everywhere on this 2D disk,
Yeah.
but we don't know the stopping time. So yeah, Hannes raised a good point. So there is a clever way to create such stopping time. There is adding an additional dimension, and we augment the data by an additional dimension z. And when following these electric field lines, we wouldn't end up at the origin, because every electric field lines will intersect with different points on the data support. Yeah.
Okay, so instead of traveling along our data dimension, we now travel along our data dimension and some additional.
And one additional dimension. Yeah. Yeah. So that's the way we get around the mode collapse issue. And in addition, we prove that such electric field lines in an augmented space actually define a bijection between the data distribution, such like this heart-shaped distribution, and a uniform distribution on a large hemisphere. So the argument is similar to the zoom out picture I just showed, because as we zoom out, this heart-shaped distribution will eventually become a single charge.
Okay, can you go a slide back?
Yeah, sure.
Do I now get it right? We have this. So here we are in our data dimensionality, and if we are in our data space currently, and we could follow our electric field lines in our data space. But if we do that, then and if we start with some randomly placed data in our data space, and then follow our electric field, then we would just end up going to having this mode collapse. But if we instead say, whenever we are in our data space, whenever we have something that's actually lies in our data dimensionality, so that's in the XY plane, then we stop. Then we no longer run our denoising, so to say. And instead, we only if we have a Z that is non-equal to 0, then we follow the electric field line.
Exactly.
So we still move a little bit into the XY directions, but we also move in the Z direction, and the Z always goes towards 0. And then sometimes we end up here, like let's say here, and then we stop. We don't continue if we have reached the XY plane.
Exactly.
So our diffusion sort of is now along the Z. Now we no longer have a time dimension, we now have a Z dimension.
Z plays a similar role as the time dimension. But later on, I will show how to unify Z and T in the PFGM++. So exactly. So when we follow these electric field lines, we can recover the data distribution by starting from a uniform distribution on the large hemisphere. So, so how do we do generation? We first uniformly sample an initial point on the large hemisphere, and then we evolve the sample by following the electric field lines. And we stop when z equals to 0. At this time, we are essentially getting a point sample from the data distribution. So before I getting into some technical details, are there any questions till now?
Yeah, well, what, for example, while the others maybe write their question in the chat or raise their hands, what, for example, happens if I now sample along the blue ring that's already at z equals 0? What would I do then during generation?
Blue, I think we wouldn't sample from the blue ring because its measure is 0.
Okay, for
Yeah.
example, to something very, very close to the blue
Then
ring.
it wouldn't move. Oh, so it wouldn't move because our later I will talk about the ODE we actually we use the ODE anchor on Z, and actually we started from a large hyperplane.
Oh,
yeah,
interesting.
We projected the uniform distribution on this hemisphere onto a Z hyperplane.
Yeah. Okay, but to be clear, it would still work if we even if we sample something very close to something very close to the blue line.
Right?
Yeah. But
in practice, it wouldn't happen, but in theory, we can still simulate it because these samples will get attracted by the electric field lines from the data. Yeah.
And now for training, can we maybe have a more intuitive explanation of training?
Okay. Yeah. Before going into training, maybe I first should bring up some technical terms. So to get the electric field lines in the augmented space, we need to solve for this Poisson equation. The source term in this Poisson equation is our data distribution augmented in this with an additional dimension z. Z is just a simple delta distribution because we only place the training data on the z equals to 0 hyperplane. That's why we can directly times our original data distribution with their delta distribution, and we don't need to exactly solve for this Poisson equation because the quantity of interest is the derivative of the potential function. Which gives us the electric field, and this is the high dimensional version of Coulomb force. And when n equals to 3, it degenerates to our familiar electric force in real world. And so this electric field will define its corresponding electric field lines by this ODE. Yeah. And once we obtain the electric field, we can move samples from the prior distribution to the data distribution. To learn this electric field, we need to first use a bunch of samples to approximate it by Monte Carlo estimator. We sample NIID data to approximate this integral, and then we use a neural network to fit.
Wait a second. So here we have these y's that you sampled from our data. You have the x tilde. What's the x tilde?
X tilde is is where we want to estimate its electric field.
Yeah. So and how do you during training? How do you come up with your x tilde?
We randomly sample points in this augmented space.
Okay, but how do you how does the sampling work?
When it shares the similar spirit as diffusion model, say when we place more density on locations near the data support and sample more gradually sparsely when.
Okay, so it's conditioned on your data, right?
Yeah.
So how concretely does it look like? How would you come up with one x tilde? Do you sample one y tilde and then condition on the y tilde, you sample the x tilde?
Yeah, something like that. Yeah.
Something like that? Or
Yeah.
what is it
actually? Yeah, because this training objective is obsolete. Because we come up with an improved one, so I guess maybe we can save the time for later discussion.
Later discuss the better training objective.
But at that time we just like sample a y concatenated with 0 and adding Gaussian noise to it.
Yeah.
And we design some special noise schedule that could place more mass on the nearby region to the data.
Okay.
Yeah, something like that.
Good.
Yeah. And we use a neural network to learn the normalized version of this electric field. And F is the neural network, and here this stuff is the empirical field calculated by our data. And the actual ODE we use is anchored on the Z dimension. Z is the augmented variable, and Z has very clean physical meaning. And previously we anchor on a very vague anchor variable T, and we don't know the starting time and the end time. But once we use some simple change of variable to anchor on the Z dimension, we can have very clean starting time and end time. The end time is just Z equals to 0. And the drift term in this ODE is the electric field in the X component divided by the electric field in the Z component. The electric field in the Z component is a simple, it's a scalar. Yeah. And using the Poisson Flow Generative Models, we achieve the SOTA results at publishing time. And when using the same architecture as diffusion models, we can not only achieve the better results, but also using significantly smaller amount of sampling steps. And PFGM is also get applied to a variety of tasks like antibody generation, medical images generation, or RNA sequence generation.
What's the antibody generation one? Do they do like generate the structure and the identity of the amino acids at the same time?
Yeah,
do you know?
I don't know the detail, but I guess you send me the paper.
Yeah, that was some time ago.
Yeah. I didn't have a close look. Yeah. So one interesting experiments we observe in our old paper PFGM is that PFGM is the only ODE-based method that can produce decent samples on a weaker architecture. The weaker architecture means that the neural network can have much bigger estimation errors. So it means that diffusion model is most susceptible to estimation errors. Why is this? Why is it the case? This is because the norm of training samples and the sigma has strong correlation in diffusion models, and the diffusion models only seeing these seeing samples in this highly concentrated region during training. But we know that neural network can have estimation error. So during sampling time, the sampling trajectory could deviate from such norm sigma relationship. And this sampling trajectory would eventually collapse to some noisy images.
Okay, but why does it then help to integrate with an SDE?
Sorry.
So if this is how
you mean why SD helps them to?
Yes.
Because SD has can counter the estimation error. It could cancel out the estimation error.
Well, if we add some noise, why does the estimation error get cancelled out?
Intuitively, how to say, let's see, how to say, explain intuitively. Let's see how to explain it. Yeah, I don't have an intuitive. I have an intuitive way to explain it, but it will take a quite long time. And yeah,
Okay.
if you want to know it, I guess we can
we still have to talk about PFGM plus today.
But let me see how to say.
Can you explain on some conditions? No, never mind.
Okay.
Not important.
Yeah.
Okay, let's continue.
Yeah. Okay.
So we have PFGM, the fusion models. We have this issue that we are basically get out of distribution of what the model has seen during training with the fusion models. And we don't have that with PFGM plus in terms of the gradient norm and in terms of the data norm. And now, what does that tell us?
Yeah. So, but the wider region of the training norm means that PFGM has to train the model on a wider span of samples, which could make the training much harder. So it motivates us to change the shape of electric field or change such norm Z or norm sigma relationship by maybe interpolate between these two models.
Okay, so to say the issue is, right, during inference, our model isn't, because our model isn't perfect, we accumulate error and maybe sometimes get out of the distribution of what the model has seen during training. Now we have PFGM where the model sees more during training, so to say. But what if we see much more than we even need during inference? Then we're doing our training inefficiently. So now can we find the middle ground between seeing everything in PFGM and seeing only a very small trajectory in diffusion models and have like the
sweet spot.
The sweet spot.
Yeah, exactly. So in our next generation Poisson flow, we changed two aspects in PFGM. The first one is the dimensionality of the augmented data, augmented variable. In PFGM, we only augment the data with one additional dimension. But in PFGM++, we can augment the data with an positive number dimension, like dimension 3, dimension 5. So we can vary the dimensionality of the augmented variables. And interestingly, when the dimensionality of augmented variable tends to infinite, PFGM++ could degenerate to diffusion models, which means that the diffusion models can be viewed as electric field in an infinite dimensional space. So as Hannes just said, actually we can find some sweet spot between 1 and infinite that balance the robustness and the rigidity. Rigidity means that we can more easily train our models, our generative models. So this is the first improvement. And the second improvement is that we don't need the large batch training objective in Poisson flow anymore. In PFGM, we need to sample a large batch of samples and then estimate the electric field But now we can, in PFGM++, we can follow the similar denoising score matching objective to get our learned neural network instead of sampling a large batch of training data. So how can we achieve it? In PFGM, we augment the data with an additional dimension z, but in PFGM++, we augment the data with additional d dimension and additional d-dimensional augmented variables. For example, in PFGM, we imagine our data is a one-dimensional line density, and we augment it with an additional dimension z. But in PFGM++, we augment the data with a two-dimensional augmented variable z1, z2, and we can still place the data on the z equals to 0 hyperplane. And so we can similarly derive the electric field in this higher dimensional augmented space. And the power of this electric field is now n plus d, because we are augmenting the data in an n plus d dimensional space. And similar to previous PFGM, now in PFGM++, the electric field lines define a bijection between the data distribution and n-dimensional hypercylinder. And we can similarly derive an ODE, but at this time, the anchor variable of this ODE is the norm of these augmented variables. And yeah, this slide is essentially saying that we can directly generalize everything we have in PFGM into a higher dimensional augmented space. Yeah, and for the training objective, in PFGM, we need to sample a large batch of samples to estimate the electric field lines. This training objective is inefficient and is incompatible with typical conditional generation setting. But in PFGM++, we can just first sample a clean data Y and perturb it by a specially designed perturbation kernel Px given Y, and we prove that when we minimizing this L2 loss, the minimizer is the ground truth electric field.
Okay, let me understand this training a little better. So we have our we sample Y from our data. Now how do I come up with my X given Y?
We sample X given Y from this perturbation kernel.
Yeah, like how does it look like computationally? If I have my Y, how do I get the X from it?
We have this conditional distribution, and we can you mean how to sample from this?
Yeah.
Okay, we can first sample from a beta distribution and then convert it to some inverse beta distribution, and then doing some change of variable to get this final distribution.
Okay.
But when d tends to infinite, this is the Gaussian.
Okay.
Yeah. So, but for finite, we can still sample from it by just establish a bijection between this perturbation kernel and beta distribution, and then first sample from the beta distribution and convert the beta variable to this perturbation kernel.
Yeah.
That's I omit those details. Yeah.
Okay, so during training, I first sample my Y from my data. First I sample my R, and this R is, so to say, a time parameter, which will tell me which perturbation kernel I use, so which noising kernel I use. And yeah, then I sampled my data, and then based on my data, I perturb it with this perturbation kernel. That's also R tells me how far I perturb it, so to say, and then I end up with my X or x tilde. Why do we have x and x tilde here?
X tilde is the augmented variable. It's just a concatenation between
okay,
x
yeah.
and r.
Okay.
Yep.
And I give then this to my network, which estimates me this x minus y.
Yeah,
And
it's
that's
similar to diffusion model, the displacement between perturbed images and clean images.
Very nice, very nice.
Yeah.
Okay.
Yeah. Okay. And this training objective dispense with large batch and is compatible with like a typical conditional generation, like text to image generation. And when d tends to infinite, as I just mentioned, this one will degenerate to Gaussian. And when we set sigma equals to r divided by square root of d, sigma is the standard deviation of the Gaussian perturbation kernel in diffusion models. And this whole training pipeline will just yields the one in diffusion models. Yeah. And here we come back to our previous norm sigma picture again. As we can see, when we increase the augmented dimensionality, our the density of the training sample norm will become more and more concentrated. But as we decrease the dimensionality, the density of training sample norm will become very long tail. So it motivates us to find a sweet spot, D in the middle, because for smaller D, it's harder to train the generative models, but for larger D, the generative model will become more susceptible to estimation errors. And is there a real sweet spot in the middle? So the answer is yes. In all of our experiments, we observe that some medium D achieves the best results across different image resolution data sets. And we test our model on CIFAR10 FFHQ 64 and LSAM 256, and we can see that some median D achieves the best results. And when D tends to infinite, this one is diffusion models, and it's called EDM, and it is the current best performing diffusion models. But our model still outperforming it. And yeah, and our model is currently the best performing model on CIFAR10 image generation dataset. Yeah, and here's the visualization of the generation process of PFGM++ from noise to clean images.
Can you stop at the end so we can look at them?
Stop at the end. Image. Yeah, I don't have.
No, well, not so important. On the next slide, we have some images anyway, right?
Yeah, this is for the CIFAR10 dataset. It's a bit low resolution, but yeah, in these experiments, we deliberately adding some noise in their sampling process, and we can see that when we add some noise in the sampling process, the diffusion model collapse. It just generates some quite noisy images, but when D is small, the model can still generate some clean images with
nice.
Even though we add some.
Oh, so here you really make this experiment. What if we are now with 64, right? We are training on greater data norms and training more inefficiently, so to say, but we're training more robustly.
Yes.
And then if we add some noise during inference with 64, we still get good images,
Yes.
while the more brittle diffusion model at infinity struggles to still generate something good.
Yeah. And we test the robustness further on post-training quantization. We quantize the neural network after training. We quantize their convolutional weights to lower bits. and we can see the gap between 64 and diffusion models widen when we use a more aggressive quantization bits.
So how does during training, how does the convergence, or how does the convergence change if we train with a lower D?
Yeah, good point. Yeah, the convergence will become slower for lower D.
Yeah, but like, I mean, it should become lower, right? But is there something that can be said about it? Is it like super bad if we train?
Not super bad, but yeah, for this model, we all I didn't examine the convergence speed carefully, but I would say I just directly borrow the setup in diffusion models and use the same training iteration. But I have examined the intermediate checkpoints, and I observed that at the early training stage, our model converges more slowly. Yeah, but eventually it will catch up the diffusion.
Okay.
Yeah. Yeah, and I guess that's it. Yeah, for Poisson flow generative models that first proposed to use the theory in electrostatic to create a new generative models, and its follow-up work PFGM++ that further expand the dimensionality of augmented variable and also adopt a more efficient training objective. And it's the current state-of-the-art models on CFAT FFHQ 64 dataset. Yeah, and thanks for listening. Are there any questions?
Okay, yes, we have some questions. For example, you know flow matching, right?
Yeah.
How does this compare to flow matching? Like for example, in flow matching, if you go to your gradient norm plot, why do I call it gradient norm? To your data norm plot here, where would like standard flow matching with a sigma during training of, right? We let's say we do linear interpolation as our conditional mean, and then we have a constant sigma around that linear interpolation.
So the prior distribution is still Gaussian.
Yeah, let's take a go.
This phenomenon will still happen.
Okay.
Because when sigma is large enough, for example, when the data is close to the prior, when the t is close to the prior, and all the samples will concentrate on a ball, on a sphere of the ball. Yeah, so its norm will still get concentrated. But it's worth to mention that PFGM could be viewed as a subcase in flow matching when we pick this perturbation kernel in flow matching. Actually, this flow matching come out later than us, but PFGM++ can still be regarded as
okay. So what we could do is use a mean. No worries. We could use a mean that's like, I don't know, some geodesic, for example, or that some path that we know is reasonable, but then use this perturbation kernel if after interpolating somewhere on this geodesic, and then we have now like solved the problem for flow matching as well.
You mean for some
so our we first have our the mean of our, and now no longer we can call it mean. We have our interpolation, our interpolant, and then we make it a stochastic interpolant by first taking time equals 0.5, the sample along our interpolant, and then we add to this sample some noise with your perturbation kernel, and that is then what we supervise.
We can do that. If at that 0.5 there's a small transition, we can design some small transition between Gaussian and this one. Yeah, we can do that.
But no, I mean we're still starting from a Gaussian, right? we still our prior is still a Gaussian, so we will still have this issue that in high dimensions everything is concentrated on a sphere, no?
Yes.
Yeah. Okay. So, but we could do flow matching also just with your perturbation kernel, and then use this as our, yeah, just sample from this distribution as our ground as our prior, and then do flow matching with that instead of sampling from a Gaussian. Okay, nice. Yeah, then we also have the question: is the model mainly used for data augmentation?
The model, you mean the generative model itself? Yeah, it can also be used for some real application like text to image generation, or like I don't know, maybe molecule antibody generation, for example. It's not limited to data augmentation.
Yeah.
Yeah.
Okay, well then, so what do you're pretty big in the diffusion model world, so what do you think of flow matching? So recently on Twitter I posted diffusion models are dead, long live flow matching or something, and then people and I explicitly put the upside down smiley there, which in my opinion is supposed to indicate sarcasm. But still, many people now ask me why would flow matching be better than diffusion models, which I never said.
I guess I would characterize flow matching in a diffusion model family.
Yeah.
Yeah.
So like how PFGM also is a.
I guess there's a general notion of diffusion model is a continuous normalizing flow that map a prior distribution to a complicated data distribution.
But then what are we calling diffusion models? Anything that's a continuous normalizing flow?
I mean diffusion model. This is like its generation mechanism. It also have chaining mechanism, which is like denoting score matching, and PFGM or flow matching, all PFGM plus and the flow matching all follows a similar paradigm. You're right. I shouldn't call everything as diffusion model, but what I mean is that this generation mechanism or the chaining paradigm lead to the new phase transition.
Yeah.
But then flow match is not another phase transition. It's under this phase transition.
I would say a diffusion model, so to say, introduced the matching paradigm. And now we have many matching models. We have the diffusion matching model. We have the flow matching models. And these are just simulation-free ways of training. Right? We don't need to simulate for training anymore. We just match very easily. And now with flow matching, or whatever you want to call it, if we no longer we no longer need to design of some diffusion, or we're no longer restricted to the forward process being a specific diffusion. Can have whatever forward process we want. That sometimes, like if we're just doing image generation, then this doesn't sound so relevant to me. Like, why not just diffuse to a Gaussian? Why would it be better to do something else?
Exactly. It's not hard to find a valid matching between certain valid matching objective and establish the bridge between like a prior and a complicated data distribution. So I guess the real question is which flow process is the best one or the better one in this task. And I guess PFGM kind of answer this question to some extent. Like there's a hyperparameter D that allow us to control this property, but flow matching didn't tell us which model it's better. It just brings out.
Oh, well, yeah, that's for images,
Yeah,
right?
yeah,
But
yeah.
what flow matching does for us, if we, and maybe also not the original flow matching paper, right? But what flow matching does for us, that we can now use arbitrary conditional flows, or yeah, arbitrary conditional flows. And we no longer have to use a diffusion as our forward process.
Yes.
And yeah, this arbitrary conditional flow for images, we don't know what would be a better conditional flow. Well, now we know that this is maybe one better conditional flow, this PFGM plus conditional flow. But for if we're doing modeling on some, want to do modeling on some manifold of some 3D structures, for example, then it's much easier to instead of now finding out what is the diffusion on this manifold and trying to find out what is the diffusion on this manifold, which can be very hard. We can now just do our find some geodesic on this manifold, add a little noise to it, and that's our conditional flow, which we use for flow matching.
If those geodesic things could be expressed as some perturbation kernel. I think so. Yeah.
Okay, friends of the sun. Any other questions? Dom, do you have some questions?
Yeah, no, it's all fine for me. I don't have any more question. Except
Very good,
perhaps like one tiny thing is like the convergence time in terms of like number of iteration to go from noise to image. Like, have you observed that any value of D is faster? I don't know.
Like for the number of integration steps that you need.
Exactly.
Can you live with fewer if some D, some certain D value?
I guess since smaller D is more robust to estimation error, so it naturally allows for larger larger step during sampling. So we do. I didn't put the result here, but we do observe that for when using smaller number of sampling steps, we have larger performance gain.
Okay, so small d means able to make small number of integration steps.
Yes.
Okay.
Small d, large steps.
Mm.
Okay. Good.
Thank you.
Friend of the sun. Then
Thanks.
I would call the day here, unless our diffusion model experts, Yilun, any last words? What do you think is the future of the world, the future of generative modeling? Any rectified flow, any stochastic interpolant, any diffusion model opinions you want to share?
I guess for diffusion models, it's I say it's an important phase transition in generative models, but it's hard to. It already exhibit quite good performance in terms of scaling, like DALI 2 stability, mid-journey things. So I would say, So, but there's another important family of generative model called autoregressive models. It also exhibit strong scaling performance. So it's hard to say which one will eventually succeed.
What do you mean
future.
with strong? Like, can you say some examples? Like, are there papers that generate images or something?
A Google recent paper.
Okay, what does that do? It generates images autoregressively, pixel by pixel. And which pixel, like random order autoregressive?
Razor scan from
don't we remember there was also like this image GPT or something, I think, that autoregressively generated images, right?
But there are also many unsolved problems in diffusion model. Is like the efficiency, how the efficiency is like how to better check the sample quality with the speed. and people previously only focused on the ODE solver because its discretization error is smaller. But as I just briefly mentioned, SDE, in SDE, the noise can counteract the estimation error. And yeah, and I guess there's also another promising direction. Yeah, sorry, I didn't explain this issue thoroughly in my talk, like why the noise can counteract the estimation error. But yeah, we have a paper called Restart. They explain this quite nicely. But I guess there is still larger room for this how to improve the efficiency of diffusion model. This is training-free improvement, and there are also larger room for distillation, like how to distill diffusion model, even just in one step, like consistency model. And this is in terms of efficiency. And there are also a large room for like improvement in controllability, because currently it seems that text to image generation has quite poor controllability. User has to explore different kinds of prompt to obtain the desired images. Yeah, and this can, and there are some interesting problems in there, and also, as I just said, others are a bit empirical, so I guess that's what I have.
Okay.
Yeah.
So many thanks to Yilun for this very nice discussion, not only about his paper, but also his view on the field, on flow matching, and all the other generative models out there. And yeah, now we can maybe be inspired by his opinions on the field, work on these things, or you can also just join us next week, where we will have another exciting paper to discuss every Monday, 11 a.m. EDT. See you then.